Assalamualaikum warahmatullahi wabarakatuh. So in this video, our team will explain about the input-output material as part of the computer organization and architecture subject. So in this video, our team will explain about 7 submaterial as part of the input-output material, which is the first input-output module definition, the second is types of external devices or peripherals, the third is peripheral device schematic, the fourth is input-output module function, the fifth is input-output module structure, and the sixth is input-output technique, and the last submaterial will be input-output mapping. So move on to the first material about input-output module definitions that will be explained by Muhammad Khairul Amtsal.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Khairul Amtsal, F1D 022064, and in this section I would like to define what is the input or output module. Okay, let's get started. So I would like to outline 3 main facts about the definition of I/O module. The first one is interface. What is interface? We would like to see the definition. So here's the definition. According to IIT article, it says that an interface is a device or system that other entities use to interact. So according to this definition, we can say it's something that abstract. It's an abstract thing. It may has no form. It may has, but it's something that two entities use to interact. So, for example, if you speak in English language, then your interface to talk with people that also use English as a native language is interface. English language is an interface for both of you to talk. Okay, that's it. And in this context, the interface itself is a device of computer that computer used to connect itself with the peripherals. Okay, so the two entities, the peripherals and the computer itself. It's a device, it's an interface that connects both of them. And then the second outline is the second main fact is it's an hardware. So we restrict the definition from the previous definition. It's an abstract thing, but in this case it's an hardware. So we know it has physical form, right? It's a hardware that bridges the peripheral with the bus. Okay, and then third one is has a set of ports. It's so to connect the peripheral with the inner system of the bus, it has some ports to connect it physically. So to easier understand this, I can show you the illustration of ports. Okay, so here's the illustration of ports. You can see here, it's a physical it has physical form. Okay, so now we have mentioned before what the term of peripheral, and we don't know what it is. We just mentioned it. So we will have to introduce you to the peripheral. What is the peripheral? So peripheral is basically a term that refers to the external device, whatever it is. If it is a external device, it is a peripheral. Okay, and there are two categories for a peripheral in the computer system, which are according to the entities which can control it. So in this case, it's a human interface device and machine interface device. Human interface device is a device that human can control. Human can use to control the device. So for example, it's a keyboard, mouse, and microphone, for example, and etc. And the machine interface is the connection between machine and machine. So it has nothing to do with human. So human can control it, cannot control it. So for example, is a magnetic tape. HDD or hard disk, or the computers itself, or something else, etc. Okay.
So move on to the next material is about the peripheral device schematic. In this slide, we can see the illustrations of input-output model, which consists of lots of things that I will explain to you. First of all, the signal control that will determine what the device should do. For example, input or read to receive or read the data, and output or write to send data to another device. And the second is signal status, to send the status of the device, whether the device is ready or error. And the third is data line, a channel for sending or receiving a sequence of bits to or from an input-output module. The fourth is control logic, which determine the activity and status of external devices. And the fifth is buffer, to temporarily hold data from or to input-output modules, usually 8 to 16 bits in size. And the sixth, the last, is transducer, which will converting data from electrical, mechanical, etc. signals into digital data and vice versa, digital data into signals. So move on to the next material is about the input-output module functions. There are 5 functions of input-output module, which is control timing, CPU communications, device communications, data buffering, and the last is error detections. First of all, control timing. The input-output module functions as a data flow regulator between internal resources, CPU, memory, and external devices. Here are the examples of data transfer procedure from device to CPU. First of all, the CPU will check the status of the data through the input-output module. Then the device will provide its status through the input-output module. If it's ready, the CPU requests the device to send data, and then the I/O module receives data from the device. Then it will send data to the CPU. The second is CPU communications. The input-output module functions as a communications medium from the CPU to external devices. Here is how it works. First of all, it will decode commands from the CPU. For example, commands for hard disks, just like read sector, write sector, seek track number, and scan record ID. And then it will report the device status. For example, whether the device is busy or is it ready. And then the last, it will check or decode the address sent by the CPU. The third is device communications. The I/O module functions as a communications medium from external devices to the CPU. It will forwarding command from CPU to device, forwarding status from device to CPU, and then forwarding data from device to CPU. And the fourth function is data buffering. The input-output module functions as a temporary data container, either from the CPU or memory or from peripherals. Data should be buffered because device speed varies widely, and also it is slower than CPU speed. And the last functions is error detections. The input-output module functions as an error detector generated by the device, for example, using the method of bit parity.
Okay, next is input and output module structure. The structure of an I/O module typically consists of the following component, like first is interface to the system bus. Interface to the system bus, this component connect the I/O module to the system bus. By this component, it's allowing to communicate between the module and the other component in the computer system. Next is interface to the external device. The I/O module is linked to external device through this interface. By this component, by the structure, it facilitates the data exchange between the module and this external device. Next, we have data register. Data register, there's a register serves as temporary storage for the data during the I/O operation, and they hold the data being transferred between the I/O module and the CPU or external device. External device and interface logic. External device and interface logic. This logic component manages the interaction between the I/O module and the external device. It includes the subcomponents such as data, status, and the control element, which facilitate the transfer of data, provide information on the status of the device, and handle the control signal. Okay, next is the data lines. These lines are used to transfer data between the I/O module and the other component, such as a CPU or external device. Next is the status or control register. This register provides information about the status ongoing the operation and can also function as a control register and retrieving control signal and from the CPU to manage the behavior of the I/O module. Then there's address line and control line. The address line are used to transfer memory address between the I/O module and the other component, and the control lines are function to carry control signal from the CPU to the I/O module, instructing it on how to perform specific operation. Next is I/O logic. This component encompasses the overall logic and the functionality of the I/O module, and it interacts with the CPU and external device through the various control data and status line, coordinating the data transfer processing. All these components work together to enable the I/O module to communicate with the CPU, external device, and the system bus. The interface component can handle the connection, the data, and the status or control register manage data storage and information exchange. And the I/O logic coordinate the overall operation of the module.
So the next material is about input-output technique. First technique is interrupt-driven I/O. Interrupt-driven I/O allows the processor to continue performing calculations while the I/O device is operating. The process is that the CPU issues an I/O command to the I/O module. While the I/O command is executed by the I/O module, the CPU will execute other commands. If the I/O module has finished executing the instructions given to it, it will interrupt the CPU that its task has been completed. In this technique, command control is still the responsibility of the CPU, both retrieving commands from memory and executing the contents of the command. There is a step up from the previous technique, which is the CPU multitasking several commands at once, so there is no waiting time for the CPU.
The way the interrupt technique works on the I/O module side is that the I/O module receives a command such as read. Then the I/O module executes the read command from the peripheral and puts the data packet into the I/O module data register. Then the module uses an interrupt signal to the CPU through the control channel. Then the module waits for its data to be requested by the CPU. When the request occurs, the model puts the data on the data bus and the model is ready to receive the next command. Interrupt processing when the I/O device has completed an I/O operation is as follows. The I/O device will send an interrupt signal to the CPU. The CPU completes the operation it is performing and then respond to the interrupt. The CPU prepares to transfer control to the interrupt routine. What is done is to store the information needed to continue the operation that was executed before the interrupt. The necessary information is in the form of processor status containing the register called PSW program status word, the location of the next instruction to be executed, The information is then stored in the system controller stack. Then the CPU will store the PC or program counter of the execution before the interrupt onto the controller stack along with the PSW information. It then prepares the PC for interrupt handling. The CPU then processes the interrupt until it is complete. When the interrupt processing is complete, the CPU will recall the information that has been stored on the controller stack to continue the operation before the interrupt. There are various techniques used by the CPU in handling this interrupt program, including multiple interrupt lines, software pool, daisy chain, bus regression. The simplest technique is to use multiple interrupt lines between the CPU and the I/O modules. However, it is not practical to use a number of bus lines or CPU pins to all interrupt lines of I/O modules. Another alternative is to use of a software pool. In this process, if the CPU recognizes an interrupt, it will go to the interrupt service routine, which polls all I/O modules to determine which module is performing the interrupt. The disadvantage of software poll is that it takes a long time because it has to identify all modules to find out which I/O module perform the interrupt. Assalamualaikum warahmatullahi wabarakatuh. My name is Zelena Mardita with student ID F1D022103. Now I'm gonna explain about input-output technique. A more efficient technique is daisy chaining, which uses hardware pool. All input-output modules are connected to the CPU interrupt channel in a chain. If there is an interrupt request, the CPU will execute an acknowledge signal that runs on the interrupt channel until it finds the input-output module that sends the interrupt. The next technique is bar arbitration. In this method, the input-output module first obtains bus control before it uses the interrupt request channel. Thus, there will only be one input-output module that can perform interrupts. Next, there is direct memory access or DMA. Configuration is the process of configuring a computer system to transfer data directly between input-output device and main memory without going through the CPU. This allows input-output device to transfer data independently, thereby increasing the efficiency and speed of data transfer. The following are the general steps to perform DMA configuration. 1. Identify the DMA ports to be used. There are 8 DMA ports, namely DMA0 to DMA7. 2. Determine the DMA transfer mode to be used, namely single mode, or block mode. In single mode, DMA will transfer 1 byte at a time, while in block mode, DMA will transfer a number of bytes at a time. 3. Specify the memory address to perform the data transfer. The DMA will transfer data from or to the specified memory address. 4. Specify the input-output port address to perform the data transfer. The DMA will transfer data from or to the specified input-output port. 5. Specify the number of bytes to transfer. The DMA will transfer the specified number of bytes. 6. Configure the DMA controller. Every computer system has a DMA controller that manages the data transfer between the input-output device and the main memory. This configuration can be done through the BIOS or through an application program provided by the computer system vendor. After the DMA configuration is complete, then input-output device will be able to transfer data directly between the input-output device and the main memory without going through the CPU. This will increase the efficiency and speed of data transfer in the computer system.
Okay, next is the input-output mapping. First is memory mapped I/O. Memory mapped I/O is a type of I/O mapping where the same address space is shared by both the memory and I/O device. This means that the available address space for the memory is reduced because the some address are allocated to I/O device. In memory mapped I/O, the CPU treats the I/O device as if they are regular memory location. There are no special instructions dedicated solely to the I/O operation. Instead, the CPU uses a similar instruction as those used for the memory access. In simple terms, memory mapped I/O allows the device to be accessed using memory address. The CPU can read from and write to this memory address to interact with the I/O device. This approach simplifies the programming and control of the I/O operation because the CPU can use the same instruction and the technique it used for accessing memory. It eliminates the need for separated I/O specific command, making the system more streamlined and efficient. Okay, next is the advantage of memory mapped I/O. Faster I/O operation. Memory mapped I/O allows the CPU to access the I/O device at the same speed as accessing a memory. Next is the simplified programming. The simplified programming, there is no need to specialize the I/O instruction, reducing the complexity and making development can be easier. Okay.
Right, so we move on to the second configuration, which is the isolated I/O. So isolated I/O is characterized by the by these two things, which are have common bus data address for I/O and memory, and the second one is separate read and write control lines for separate address space. So here's one. I'm going to show you the illustration. Yeah, like I mentioned before, it's like I mentioned before about the isolated I/O. So it has a it has a common bus line in here. You can see here it has a common line bus for memory and I/O, but it has a different branch on the address. So for memory, this is the address for address bus and the data bus, and this part has a different control lines and address space. So what's the advantage of this configuration is it allows the CPU to make operation for different device. Like it can make an operation twice for these two device in a time. So this isolation may in the I/O give the advantages that, well, what if hypothetically if something more happened in the I/O operation, then because it's isolated, then it's not gonna affect the other device such as memory or something like that, because it's isolated, right? That's the advantage of using this configuration. Right,
So I think there's so I think that's all for the explanations of input-output material in these videos by our team. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.